Hello everyone, this is Manohar Reddy, Department of Cybersecurity, Institute of Aeronautical Engineering College. So today I am going to discuss about the concept of groups and its types. So in the previous sessions we discussed about algebraic structures, definitions, algebraic systems, properties. So the properties which are applicable to the all different types of algebraic systems and algebraic structures. So today the one of the form algebraic structure is to be called as group. So today we are going to discuss about that groups and its types. Right, let me look here. So groups. So generally groups are nothing but a collection of elements or set of elements. So in this algebraic system point of view, a group must be having some different types of elements, and that consists of a different order. And it should follows closed operation, associative operation, identity operation, and inverse operation. These are all nothing but properties of the algebraic system, algebraic structure. So group an algebraic system G comma star. G indicates the group name as well as star indicates the operation performed on all the elements. So G comma star is said to be the group if the following conditions are to be satisfied. If closed operation should be satisfied, associative operation should be satisfied, identity operation should be satisfied, and inverse operation should be satisfied. If it satisfies all the operations, then it is said to be the group. So G equals to 1, 2, 3, 4, 5, 6, 7. These are all the elements. In the group. You can say that these are all the elements, these are all the values of this group contains. If this group can have these types of elements, so then you can say that G is a finite group. The name itself finite means you can count the number of elements in this group. If you are not able to count the number of elements in the group, that means G equals to 1, 2, 3, 4, 5 up to infinity, then you are not able to count the elements. So then G is a infinite group. So G is a finite group, is also called as non-empty set group. Non-empty group or non-empty set. Non-empty group, because the group contains some values. If that group doesn't contains any values, then you can say to be the group is empty group. Or else you can set you can write empty set also. The values in the group is called as finite group or order of a group also, you can say that. And if the elements doesn't have in the group, then you can say that empty group. That is nothing but empty group or empty set. That indicates G equals to pi also. Means doesn't have any elements. So it indicates pi also. Null set or null group. Right. So G is an infinite group. So why we are talking about this all the things means you are going to perform this all the operations if and only if the group contains elements. If the group doesn't have any elements, you are not able to perform this all the operations. So that's why we have introduced this finite groups, infinite groups, non-empty set and empty set groups. Right. So you can perform this all the operations on these groups only. So closed operation. So in the closed operation, what we said, like, so if A plus B belongs to the group, A plus B value or A star B value belongs to the group, then it's said to be the group is a closed operation. And associative operation. For the associative operation, we know that A plus of B plus C equals to A plus B of plus C. Then we can say that it is a associative operation. The value I'll get from the left side is equals to the value I'll get from the right side. Both are should be equal, and that values are related to this group only. Then that values are related to this group only. So that you can say that it is an associative. And the next one is identity operation. So identity with respect to the plus operator, you can say that E equals to 0 as the identity element, and with respect to the multiplication, E equals to 1 as the identity element. So if you take any of the expression A plus E equals to A, because the identity element E equals to 0. E equals to 0 that we taken. So it performs identity operation whenever if E equals to 0 on a plus operation, then it is said to be the identity. Similarly, A star E equals to A with respect to the plus star operator, where E equals to 1. E equals to 1. This is the identity element 1 with respect to the multiplication, and E equals to 0 with respect to the addition operation. So it satisfied identity property also. And next one, every element in G has universe. So G has universe means A plus of minus A. See here, the minus A is the universe element of A with respect to the plus operation. We have to get A plus minus A equals to 0 definitely, or else A star A universe equals to 1, because here the universe A universe is the inverse element of this A. So that we will get A star A inverse equals to 1 with respect to the star operator. Similarly, A plus of minus A, here A minus A is the inverse element to this A. So that's why we mentioned that A plus of minus A equals to 0. So with respect to the plus operator. So identity element is what? E equals to 0, E equals to 1. Similarly, here the inverse elements, the inverse values of the integers minus with respect to minus A with respect to the plus operation, and inverse A inverse is inverse element to the A with respect to the star operation. So like the way you can understand this, all the operations performed on the groups. So if and only if it satisfies these all the operations on this set, then you can say that this set is to be the group. Definitely you can say that it is a group, because this set performs a closure operation, this set performs associative operation, this set performs identity operation, and this set performs inverse operation. So performing all these operations belongs to this set is called as group, right? And next, the groups can have a different types, like groups contains subgroups, semi-groups, cyclic groups, monoid groups, and modulo groups, and abelian groups, right? So these are all the different types of groups by performing different operations on the different sets. So some of them are performing all the operations, some of them performing only limited operations. So based on that operations, we are going to know that each and every one as a subgroup or semi-group or monoid or something. Now we'll see. So the next one is what? Abelian group. So abelian group is also called as commutative group. So abelian group is also called as commutative group. The name behind this commutative group, that abelian group performs commutative rule. So A star B equals to B star A. Here A comma B belongs to G. Suppose 1 and 2, that equals to 2 into 1. So 2 into 1 equals to 2. So that this 2 belongs to this group only. So this is the commutative formula, and if it satisfies this commutative, then that abelian group is said to be commutative group also. So commutative group or abelian group are both same. But if you mention this commutative law, then you can say that group is commutative group or abelian group, right? So and abelian group contains these are all the formulas to be satisfied, like the group also. See, every group is a subgroup or abelian group or semi group or monoid, anything, but all the subgroups, monoids or semi groups are not become as a group, right? So not become as a group, because group contains to be satisfied all the rules, but subgroups or semi-groups or some groups can follow only certain formulas. So see here the properties. Identity element is unique. So it wants to be abelian group, then identity element is to be unique, and the inverse of element is unique. Inverse of an element is unique. Along with this, it follows this De Morgan law, and left cancellation law, right cancellation law, left cancellation and right cancellation. So left cancellation and right cancellation is what means. See here, A star B equals to A star C. From this expression, you can see the values A value, B value, C value. So here the left side of the elements A comma A, the left side of the elements are A comma A has to be cancelled by using this left cancellation law. So then the result will become like B equals to C. Then the result will become B equals to C by cancelling these left variables. Left variables are left values, you can take any of them. And similarly, right cancellation law. So right cancellation law, A star C equals to B star C. In this expression, you can observe these right variables are C, C. So you can cancel them directly by applying this right cancellation law. So that you will get A equals to B. A equals to B. So you have to show that A equals to B by applying this right cancellation law, and B equals to C because of you applying left cancellation law, right? And A star B whole inverse equals to A star B whole inverse equals to B inverse star A inverse. So this is nothing but De Morgan laws. So you have to understand this one. And in the group, the identity element is its own inverse. The identity element is its own inverse. That means this is an element, and the identity element of this is its own inverse. So A star A inverse equals to 1. That is, this is nothing but its own inverse value. Or else you can say that A plus of minus A. So here minus A is the own inverse of this value. But A plus of minus B is not possible. A plus of minus B is not possible, and similarly A star of B inverse is also not possible. These two are not possible for this inverse. These two are not possible for this inverse operation. So this is the way you can understand this abelian group. If any set, suppose G equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the set, then if it wants to be abelian group, then you have to show them it satisfies commutative law, and identity law, inverse law, and left cancellation and right cancellation laws. Along with this, associative follows. Along with this, all this group follows. So if it follows this all the formulas, if it follows this all the rules, then it is said to be abelian group. So this is the way you can understand. See here that example. Show that the set of all integers z equals to plus or minus 1, plus or minus 2, plus or minus 3. So up to, you can take any of them. So all integers is an abelian group with respect to the addition operation. So addition operation, it is we are going to show that addition operation, this set becomes as an abelian group. So you see here, let z equals to set of all integers. Let A comma B comma C are any three elements of Z. You can take plus or minus 1, plus or minus 2, plus or minus 3. You can take this is A value, and this is B value, and C value. You can take, And for the closure property, it should the sum of two integers is again an integer. So sum of two integers is an again integer. That is nothing but 1 plus 2 belongs to z. So 1 plus 2 is what? 3. 3 belongs to z. So if satisfies 3 belongs to z is also there, but so then you can say that a comma b belongs to z. Then it is said to be closure property. And next, associativity property. So associativity properties means what? So a plus of b plus c equals to a plus of b plus c. A plus of b plus c. So here a plus b of plus c is equals to a plus of b plus c. You can pronounce it as a plus b of plus c equals to a plus of b plus c. So the value of a plus b 1 plus 2 plus c is what? 3 equals to a 1 plus of 2 plus 3. So what you will get? 1 plus 2 is nothing but 3 plus 3, and 1 plus 2 plus 3 is nothing but 5. So 3 plus 3 is nothing but 6, 1 plus 5 is nothing but 6. So hence it satisfies that associative property, and 6 is also an integer. 6 is also an integer related to this group. So you can say that it is satisfied associative property. And identity property. So identity property, we have a 0 belongs to z, and a plus 0 equals to a. Here the element 0 is the identity element for all a belongs to z. So, and inverse. So for the inverse, we know that a plus of minus a. So we know that minus a is also related to this integers. So minus 1 is also in the integers group. So that you can say that a plus of minus a equals to 0. So each element in Z has its own inverse. So it becomes inverse property satisfied, and it wants to be abelian group also. And commutativity property. So we already know that first property, combinative property. So here a plus b, the value of a plus b is equals to b plus a. Suppose you will take 1 plus 2, then b plus a, 2 plus 1, that is nothing but 3, 3. So the 3 is belongs to z, so that you can say that it satisfied commutativity property. It satisfies commutativity property. So if it satisfies, if this set is satisfied all these properties, then you can say that the set of all integers is an abelian group with respect to the addition. With respect to the addition, like the way you have to show them to be the proof. Okay. So that is the way you can do the problem. And next, the concept is what? Order of a group. We already said that order of a group. So a group G equals to 1, 2, 3, 4, 5, 6. And this is a group, and the number of elements in a group is called order of the group. So the number of elements are how many? 6 elements are there. So 6 is the order. 6 is the order of the group. Order of the group. So the definition, it indicates that the number of elements in the group is said to be the order of a group. And this order of a group is also became finite group. If the order of a group G is finite, finite is nothing but you can count the number of elements in the group. You can count the number of elements in the group. So then G is called finite group. G is called a finite group. In a group G comma star, in a group G comma star, so prove that A star B whole inverse equals to B inverse into A inverse for all A comma B comma G. A comma B belongs to G. So this is what we are going to prove it. See, we'll consider that. So we'll take A star B whole inverse. A star B whole inverse equals to A B inverse into A inverse. This is what I am going to prove it, right? So see here. So how we are going to prove it? So you can apply, yes, you can multiply them A star B. So A star B into B inverse star A inverse. A star B into B inverse star A inverse. So you can write this statement as what? A star of B star B inverse star A inverse. A star of B inverse star A inverse. So from this, A star of B star B inverse is nothing but E, because this is an identity, this is an inverse property, right? So B star B inverse is nothing but inverse and A inverse. So from here, A star E equals to A star E equals to A star A inverse. This is from identity element. So A star E equals to identity property. And so A star E equals to A. Then A star A inverse is equals to what? A star A inverse is equals to E. So this is the way you have to prove this from left side. And similarly, you can prove from right side also. So B inverse. So B inverse into A inverse. B inverse into A inverse star A star B. A star B. See here. B star B inverse. So we can rewrite it as a B inverse star of A inverse star A star B. Star B. From here, A inverse star A equals to E. We know that as per the inverse property. And you can rewrite it as C. And similarly, B inverse star E star B is nothing but B. We already know that identity property. And B inverse star B equals to E from inverse property. So left side is equals to E value and right side is equals to E value. So that LHS is equals to RHS. So like the way you can prove the this formula. A star B whole inverse is equals to B inverse star A inverse. Like the way you can prove it. Okay. The next one, see here. The next group. The next group in a group G comma star. If A star B whole square equals to A square star B square. So here A comma B belongs to G, then show that G is an abelian group. Show that G is an abelian group. We want to show that. So see here. First of all, you can take A star B whole square equals to, you can write A star B whole square equals to A into B star A into B from the left side. And similarly, take the from right side A square into B square. So you can rewrite it as A square means A into A star B square is nothing but B into B from the right side, right? So from here, A star of B star A, you can separate it, B star A star B, you can rewrite it. Similarly here also you can rewrite it A star of A star B star B here from this side. And here you can see that by using left cancellation law, you can cancel these two values. See here, from this point of view, you can cancel left side A by using left cancellation law, right? So after cancelling that left values, what you will get? So B star A star B, that equals to A star B star B, right? So from this expression, what you need to do again, so this B and this B is both are equal, so that you can cancel this B and B as per the right cancellation law, So those two are cancelled, and the remaining value is what? B star A equals to A star B. B star A equals to A star B. Hence it becomes, so we know that, right? We know that what? B star A equals to A star B, then A comma B belongs to G as per the commutative property. It becomes commutative group. So it becomes commutative group. So that commutative group is nothing but abelian group. Right? So if it comes like commutative group, it is also said to be the abelian group. So like the way you can prove this formula, abelian group, right? Okay. And next, semi-groups. See, semi-groups are nothing but the name itself semi. So some of the properties to be satisfied as the numbers. So an algebraic system A star. So semi-groups are indicating A. So A star is said to be the semi-group if star is a closed operation on A and star is an association operation on A comma B comma C. So if it satisfies closed operation and if it satisfies associative operation, both two operations are enough to become as a semi-group. Those two operations are satisfied, then it becomes as a semi-group. So you can see examples n plus, so natural integers n equals to 1, 2, 3, 4, 5 up to 6. You can take any of them. So taking these values and substituting this closed operation and associative operation, definitely it satisfies. So that you can say that n plus is a semi-group and n dot operator is also a semi-group. N dot operation is also a semi-group. Suppose nothing but, so n equals to, suppose I will take n equals to 1, 2, 3, 4, 5, 6. So first of all, what is meant by closed operation? We know that a plus b or a dot b belongs to n. So a plus b or a dot b belongs to n. So then it is to be semi-group. It is said to be the closed operation. It is said to be the closed operation. So what we will get to see, a value is 1 plus 2. So 1 plus 2 is nothing but 3. So 3 belongs to n. Yes, 3 belongs to n. It's right. So similarly, a dot b. A dot b is nothing but 1 dot 2. 1 dot 2 is nothing but 2. 2 belongs to n. 2 belongs to n is nothing but, so it's closed operation. Closed operation. So it satisfied closed one. And similarly, associative. Associative means what? A plus of b plus c equals to a plus b of plus c. A plus of b plus c is equal to a plus b of plus c. So what is the value of a1 plus of b2 plus 3 equals to, similarly here 1 plus 2 of plus 3. So 1 plus 2 plus 3 is nothing but 5. 1 plus 2 is nothing but 3. 3 plus 3. And see here 1 plus 5 is nothing but 6. And 3 plus 3 is nothing but 6. So you will get the value of 6, and 6 belongs to this n. So that you can say that this is a associative operation. You can say that associative operation. So if it satisfies these two closed operation as well as associative operation, then the group is said to be semi-group. Then group is said to be semi-group. Right. And next one is what? Monoid. Next one is what? Monoid. So an algebraic system, A star. A star is nothing but semi-group. So an algebraic system semi-group is said to be the monoid if and only if it satisfies closed operation. If and only if it satisfies closed operation and associative operation, and identity operation. Right. So if satisfies these three operations, then it is said to be monoid. It is said to be monoid. So take an example. Show that the set n is a monoid with respect to the multiplication. So if semi-group becomes to monoid, then it is said to be the closed operation, associative operation, and identity operation should be satisfied. Okay. So solution is here. So first one is closure property. We know that product of two natural numbers is again a natural number. We know that, right? So product of or addition of those two numbers is again becomes a natural number. So if it becomes an again natural number, then it is said to be the closure property. So multiplication is a closure property. Suppose a dot b is nothing but 1 dot 2 and 2 dot 1, that is nothing but 2 equals 2. So 2 is again, it is a natural number. 2 is again a natural number. So that you can say that closure property. And similarly, associativity property. So associativity property is what? Multiplication of natural numbers is associative. So a dot b of dot c is equals to a dot of b dot c for all a comma b comma c. Say 1 dot b is nothing but, say b is nothing but 2 and 2 dot c is nothing but 3. So 1 dot 2 dot 3 is nothing but, and similarly a dot a means 1 dot, b is nothing but 2 dot 3. So 1 dot 2 is nothing but 2 dot 3 and 1 dot 2 dot 3 is nothing but 6. So 2 dot 3, 2 into 3 is nothing but 6 and 1 into 6 is nothing but 6. So 6 is again a natural number. 6 is again a natural number, so that it satisfied associativity property. Next, identity property. So we have 1 is an identity element with respect to the addition of multiplication operation. So we know that in the groups only, so multiplication operation, the identity element is 1, and for the addition operations, identity element is what? 0. So a dot 1 equals to 1 dot A. So the result A is again natural number, so that you can say that identity element exists, and 1 is the identity element. So now you can say that n is a monoid. N is a monoid with respect to the multiplication. With respect to the multiplication. So like the way you can understand this one. And next one is what? Modulo groups. So modulo groups. So modulo groups, the groups are performing on the numbers and the remainders are become as modulos. That remainders are nothing but modulos, we know that. Right, so modulo groups can have two types. One is addition modulo and second one is multiplication modulo. One is addition modulo and second one is multiplication modulo. So addition modulo indicates like this: a plus b. Here the plus with modulo, and similarly a star b. So a star b, here the multiplication modulo. So this is multiplication modulo and this is an addition modulo. So addition modulo and multiplication modulo. So we'll see so how those two, addition modulo and multiplication modulo, works. So if you'll take 3 plus the modulo value is 5, 3 plus 4. So what is the value you will get? So 3 plus 4 is nothing but 7, obviously 7. So 7 mod 5 is what? 7 mod 5 is what? So 7 mod 5 is 2, because you need to divide 7 with 5. So 5 1 is 5 and 7 minus 5 is nothing but 2. So you will get 2. So like the way you can perform addition modulo. And for the multiplication modulo, if suppose 3 star 5 4, if it is given like this, so 3 star 5 of 4, so 3 into 4 is nothing but 12. 12 modulo 5 is nothing but what? So 12 modulo 5 is nothing but 5. You can divide 12 with 5, so 5 2s are 10 and the remainder is 2. So that 3 star 5 4 equals to 2. So the result of 3 comma 4 is to be the 2. See whether we'll check. So if 5 plus of 2 4 is what? So 5 plus 4 is nothing but 9. If you divide 9 with the 2, so 2 4 ja 8 and 9 minus 1 1. 9 minus 8 1. So the value is what? 5 plus modulo 2 4 equals to 1. Similarly, you can perform on multiplication operation. So what you will get? 5 into 5 into 2 of 4. So 5 into 2 of 4 is nothing but 5 into 4 20. So you can divide 20 with the 2. So then you will get what? 0 as the remainder. So 5 star 4 equals to 0 is the modulo value, and 2 star 2 equals to 4 with respect to the 5. So like the way you can perform multiplication modulo and addition modulos. We'll see one example. So multiplication modulo and addition modulo. So let us take a group G equals to 0 1 2 3 4 5 is a group with respect to the addition modulo 6. See how we are going to construct this table, composition table. So we'll see. So definitely you can take from this point of view. So this is the plus 6 modulo, and you can take the values 0 1 2 3 4 5. Similarly from this side 0 1 2 3 4 5. Right. After constructing this composition table, you need to give all the values. So 0 plus 0 as usual 0, and 1 and 2 2, 0 plus 3 0 plus 0, 0 plus 1, 0 plus 2, 0 plus 3. So you will get all these values. Similarly for the 1 and 1 plus 0, 1 plus 1 2, 1 plus 2 3, 1 plus 3 4, 1 plus 4 5, and 1 plus 5 is nothing but 6. So 1 plus 5 is nothing but 6. So 6 modulo 6 is nothing but what? 6 divided with 6. That equals to 6 1 is 6. So the modulo of 6 is nothing but 0. So you will get 0 here. So that is what we'll get here. And similarly 2 plus 0 equals to 2. 2 plus 1 equals to 3. 2 plus 2 equals to 4. 2 plus 3 equals to 5, and 2 plus 4 equal to 6. 6 modulo with addition modulo with 6 is nothing but 0. So 6 divides with 6 is nothing but 0, and 6 plus 2 plus 5 is nothing but 7. So 7 modulo with 6 is nothing but, you will get the value 1. Right, and similarly 3 plus 0 is nothing but 3, and 3 plus 1 is nothing but 4, 3 plus 2 is nothing but 5, 3 plus 4 is nothing but 3 plus 3 is nothing but is 6. 6 modulo 6 is nothing but 0, and 3 plus 4 is nothing but 7. 7 modulo 6 is nothing but 1. 3 plus 5 is nothing but 8. 8 modulo 6 is nothing but 2. 8 modulo 6 is nothing but 2. Right. So next 4 plus 0 is nothing but 4. 4 plus 1 is nothing but 5. 4 plus 2 is nothing but 6. 6 modulo 6 is nothing but 0. And 4 plus 3 7. 7 modulo with 6 is nothing but 1. And 4 plus 4 8. 8 with divide with 6. 6 1 is 6 and 2. So the 2 will get here. And 4 plus 5 9. So 9 you will get with the divide of 6 1 is 6 and 9 3. So 3 is the remainder. So and similarly for the 5 plus 5 is 5 plus 0 is nothing but 5. 5 plus 1 is nothing but 6. 6 is nothing but 6 modulo 6 0. So you'll get 0. And 5 plus 2 7. So 7 modulo with 1 6 1. 5 plus 3 8. 8 modulo with 6 2. And 5 plus 4 9. 9 modulo with 3. Yes, you will get 6. 9 modulo with 6 3. And 5 plus 4 5 10. So 10 modulo with 6 4. So like the way you will get all these values. So from this slide you can see here the closure property. Since all the entries of the composition table are the elements of the given set. So here you can see all the elements what you will get here in this table, all the elements what you will get here in the composition table are all belongs to this group, so that you can say that it is a closure property. And next, associative property. So the binary operation modulo 6, addition modulo 6 is associative. If you can see this. 2 plus 3 of plus 4 is nothing but 5 plus 4 of 6 equals to 3. So the value we will get with the addition modulo from the left side is equals to the value we will get from the right side with the addition modulo is to be the same. So from the left side and from the right side you will get the same values, so that it is satisfied associative property. And identity property, here the first row of the table coincides with the top row. The first row of the table coincides with the top row of the table. So top row of the table, what the elements are contains, the first row is having same the elements, the element heading that row. So 0 is the identity element. And inverse, so from the composition table we see that the inverse elements of 0 1 2 3 4 5 are 0 5, because we are going to see here wherever the element 0 appears, so those are all the inverse elements of this value. So from here the 0 comes here at 5th place, and here 4th place, and here 3rd place, and here 2nd place, and here 1st place. So 5 4 3 2 1 are inverse elements of 0 1 2 3 4 5. So this is what we are going to see here. So for these elements, these are the inverse elements with respect to the addition operation. And last, commutativity group. So the corresponding rows and columns of the tables are identical. And that means both are same. The number of rows and number of columns count is same. Therefore, the binary operation plus 6 is commutative. G plus 6 is an abelian group. So that you can say that G plus 6 is an abelian group. So this is the way you can perform these modulo groups. and to become a group or to become a abelian group, right? So this is the way you can understand all this concept. Okay, so this is the way you can understand this addition modulus and the multiplication modulus, right? Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.